class O. Let's go. Sharing my screen. So today I'll make this look not terrible. Okay. Yep. Maybe a little light. Yeah. Okay. Today for class O, we're going to be talking about more trig identities. Specifically, we're going to be talking about the angle sum identities, really the angle sum and difference. They're really the same, but we think of them differently. Identities, and then also identities, and the double angle identities. Again, which are really kind of the same as the angle sum ones, but we think of them a little differently. So let's just start off by stating the angle sum identities, and then we'll state all four of them, and I'll show you how to write them in a condensed way. Lighting here is moderately terrible. Hopefully that's a little bit better. So angle sum. So here are the angle sum identities. We will verify them with some examples. I'm just going to state them. So the angle sum identity for sine is that sine of alpha plus beta, so we write a plus b, is equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Some people write this part as sine first, cosine second. It doesn't matter. And then for cosine, we have that cosine of alpha plus beta is equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. The angle difference formulas, or the angle difference identities, which again, we're really going to just condense them into two formulas. So the angle difference identities look like this. They're almost the same as these. We're really just going to change the plus or minus signs. So for sine of alpha minus beta, it's going to be sine of alpha times cosine of beta minus cosine of alpha times cosine of beta. And for cosine of alpha minus beta, it's going to be cosine of alpha times cosine of beta plus sine of alpha times sine of beta. So often when people write these in the kind of most condensed way that they can, we usually write them as the following. We say that sine of alpha plus or minus beta is equal to sine of alpha times cosine of beta plus or minus cosine of alpha times sine of beta. So in this formula here, the signs are the same, right? It's a plus here, it's a plus here. If it's a minus here, it's a minus here. On the other hand, for the cosine formula, for cosine of alpha minus or plus beta, it's going to equal cosine of alpha times cosine of beta plus or minus sine of alpha times sine of beta. So here the sign changes. If it's a minus here, it's a plus here. If it's a plus here, it's a minus there. And I've written the formulas, I don't know, in what I would say is kind of the typical way. Cool. So let's look at a couple of examples of angles we already know. For example, what if I said I want to calculate, where's my examples here? Sure. Let's say we want to do sine of 30 degrees plus 120 degrees. Now we could do this the normal way and say, oh, well, that's equal to sine of 150 degrees. I'm in quadrant 2. My reference angle is 30. I know that for 30 degrees, the opposite's 1, the hypotenuse is 2, the adjacent is √3. Sine of 30 is 1/2, so sine of 150 is positive 1/2 because sine is still positive in the second quadrant. But if I use the formula for the angle sum, I can do this as well. Sine of 30. Now it's more work to do it this way. Sorry. But the point is to actually see that the formula works. So that's going to be sine of 30 degrees times cosine of 120 degrees plus cosine of 30 degrees times sine of 120 degrees. Let's see if it works. So sine of 30 degrees, we just said it was 1/2. Cosine of 120 degrees, well, cosine of 60 degrees is 1/2. So cosine of 120 is negative 1/2. And then that's a 30 there. Cosine of 30 degrees, that's going to be a √3/2. And then sine of 120 degrees, well, sine of 60 is √3/2. So sine of 120 is also positive √3/2. So I have a 1/2 times negative 1/2, which is a negative 1/4. And a √3/2 times √3/2, which is a positive 3/4, which equals 2/4, which equals 1/2. Check. So these are equal. We can see that the formula is actually true. Let's do one more example of kind of verifying that these are true. So let's look at something like cosine of, that seems unexciting. Let's do 150 degrees minus 60 degrees. Okay, so yeah, so cosine of 150, we can see from this triangle here, 150, right, is this angle. Oh, I should write out the formula first, sorry. So that's going to be cosine of 150 times cosine of 60 plus, right, because the signs change for the cosine formula, the signs stay the same for the sine formula. Sine of 150 times sine of 60. All right, so cosine of 150, since that's in quadrant 2, is going to be negative. So cosine of 150 is going to be negative √3/2. Cosine of 60 degrees is going to be positive 1/2. Again, right, 60 degrees is like up here. And that's where the cosine value is smaller and the sine value is bigger. Okay. Plus sine of 150, well, if cosine of 150 was a √3/2, sine of 150 has to be a 1/2. And it is a positive 1/2 because again, we're in quadrant 2. Sine of 60, well, if cosine of 60 was 1/2, then sine of 60 is √3/2. Those always go together. One of them is a plus or minus 1/2, one of them is a plus or minus √3/2. We're talking about sine and cosine. So it's going to be a positive √3/2. And if we look at this, we're going to end up getting negative √3 times 1 over 2 times 2 plus 1 times √3 over 2 times 2. And negative √3/4 plus √3/4 is going to be 0. Does that check out? Let's see. Well, 150 minus 60, that's cosine of 90 degrees. And if we look at our unit circle here up at the top, that point there is 0, 1. The x coordinate is 0, so cosine 90 degrees is 0. So this checks out. There are more complicated ways using the law of cosines to actually prove these formulas, these angle sum and angle difference identities. We're not going to do that. We're just going to kind of see that we've seen a couple of examples where it works and believe that it works for any pairing of angles, and it does. You might be asking yourself, well, why would you do this, right? Finding sine of 150 is way easier, like just doing it the normal way versus breaking it up into two angles that add to 150. Well, the point of this is that we can then use these formulas to find sine and cosine of other angles that maybe we hadn't been using before. For example, sure, let's do, excuse me, cosine of 75 degrees. Well, I can find two angles that add up to 75 degrees. I can write this as cosine of 30 degrees plus 45 degrees. And now I can use my angle sum formula for cosine. This is going to equal cosine of the first angle times cosine of the second angle minus, right, because these always change for cosine, sine of the first angle times sine of the second angle. Okay, and then this is where we really need to know our triangles or our unit circle, whichever way you want to do it. Cosine of 30 is √3/2. Right? If we want, we can draw the little triangle. Like there's our 30-degree angle, opposite's the smallest, hypotenuse the biggest, adjacent to the medium length. And then for our 45, 45, 90, All right, we've got our root 2, root 2, 2. So cosine of 30 degrees is root 3 over 2. Cosine of 45 degrees is root 2 over 2. Minus sine of 30 degrees is 1/2. Sine of 45 degrees is root 2 over 2. Now, this does simplify, and it simplifies in kind of a very specific way. Root 3 times root 2, you just multiply the inside together and you get the square root of 6. 2 times 2 is 4. And 1 times root 2 is just root 2, and 2 times 2 is 4. And this becomes one fraction, root 6 minus root 2 all over 4. It does not simplify any further. There is no good way of simplifying root 6 minus root 2. If you really, really wanted to, you shouldn't. You could factor out a root 2 from both of them and write it as root 2 times root 3 minus 1. But that's no, we don't want to do that. This is the best, nicest way of writing the answer. And what I'll say is for any angle like this, where you can write 75 degrees as the sum of two angles that we kind of know, or the difference of two angles that we're going to deal with, it's always going to look something like a positive or a negative root 6 plus or minus root 2, all divided by 4. Let's look at a couple more examples. Let's look at, sure. Oh yeah, let's do that. Let's do sine of negative 15 degrees. So I'm going to think of this as a difference. I'm going to think of it as sine of 30 degrees minus 45 degrees. So I'm going to write that as, well, angle difference formula for sine. So it's going to be sine of the first angle times cosine of the second angle. For sine, the signs stay the same. I know it's terrible that the trig function sine and the word sine sound the same. The plus or minus is going to stay the same. So it's going to be a minus here. And you're going to get cosine of 30 degrees times sine of 45 degrees. So let's see, sine of 30 degrees is 1/2. Cosine of 45 degrees is root 2 over 2. Cosine of 30 degrees is root 3 over 2. And sine of 45 degrees is root 2 over 2. Simplifying, we get 1 times root 2 over 2 times 2 minus root 3 times root 2 all over 2 times 2. And then writing it as one fraction, we get root 2 minus root 6 all over 4. Cool. Let's do a couple more examples using radians with some bigger angles. So let's say we want to find, sure, let's do cosine of, yeah, let's make it real negative. Let's do cosine of 11 pi over 12. So here's my trick for doing with radians. First of all, the angles we're going to see in radians are always going to be something pi over 12, which is kind of the way it always works for these ones where you're writing it as a sum or difference of known angles. And I have found that the easiest way to deal with this is to break it up into pi over 4 plus some other stuff. So ideally here, you're going to say that 11 pi over 12 is going to equal pi over 4 plus whatever. Really, I'm just going to get a common denominator. I'm going to say that 11 pi over 12, well, pi over 4 is equal to 3 pi over 12. And then I still need another 8 pi over 12 to get to 11 pi over 12. And what should always happen if you use pi over 4 is that whatever is left over and whatever you have here, both of those should reduce to angles that look more familiar. I can think of this as pi over 4 plus 8 pi over 12 reduces to 2 pi over 3. And if you really prefer radians, you could think of this as 45 degrees plus, let's see, 2 pi over 3 is 2/3 of pi, 120 degrees, which is 165 degrees, which is what 11 pi over 12 would become in radians, or in degrees. I'm not going to do that, but you could do that if you really prefer. Again, I think it's good for you to practice thinking in radians and not changing to degrees. All right, so here, I'm going to write this as cosine of, I like to break it up like this. I'm going to write it as cosine of pi over 4 plus 2 pi over 3. And then, okay, it's cosine, so I know it's cosine, cosine, sine, sine. And then a plus here means it's going to be a minus in the middle. So it's cosine of my first angle times cosine of my second angle minus sine of my first angle times sine of my second angle. Okay, cosine of pi over 4 is always easy. Cosine and sine of pi over 4 are always going to be root 2 over 2. So it's going to be root 2 over 2 times, Cosine of 2 pi over 3. Let's see. I know that cosine of pi over 3 is 60 degrees. Cosine of 60 degrees is positive 1/2. Cosine of 2 pi over 3, which is in the second quadrant, is going to be negative 1/2. Minus sine of pi over 4 is root 2 over 2. And I know that cosine of 2 pi over 3 was a negative 1/2. So sine of 2 pi over 3 is going to be either a plus or a minus root 3 over 2, right? They always go together. If cosine of an angle is 1/2, sine of the same angle is going to be either root 3 over 2 or negative root 3 over 2. So ignoring the signs, if one of them is something 1/2, the other one's going to be something root 3 over 2. So here, sine of 2 pi over 3, well, it's going to be positive root 3 over 2 because 2 pi over 3 is in quadrant 2 and sine is positive in quadrant 2. So then writing this out, this one, I would feel like it's a little bit funky. It's going to be negative root 2 over 4 minus root 2 times root 3 is root 6 all over 4. This is going to be, I prefer to write it as negative root 2 minus root 6 all over 4. Some people prefer to write the minus sign out in front and write it as negative, and then it's going to be root 2 plus root 6 all over 4. If you multiply that negative 1 to the top, it distributes to the root 2 and to the root 6. So I like this, but if you prefer this, you can write it that way. Just be careful, right? The negative out front means a different thing than the negative in front of the first term in the numerator. I know it's kind of, it's annoying. Let's look at another example. Let's look at something like sine of, sure, let's go big. Let's go 23 pi over 12. Almost a full 2 pi. So, oh, I actually already did this one. We kind of did this one when we did sine of negative 15 degrees. Let's change it up. Let's make it sine of, sure, let's go, I'm tired of doing ones in quadrant 2. Let's go quadrant 3. Let's go 13 pi over 12. And again, I'm going to think of 13 pi over 12 as just pi over 4, which is 3 pi over 12 plus the rest, 10 pi over 12. Reduce those fractions. That's going to be sine of pi over 4 plus 5 pi over 6. That's going to be, so the sine formula, it's sine of the first angle times cosine of the second angle plus cosine of the first angle. So then that was in quadrant 2, oh well. And then sine of the second angle. So my reference angle, so the pi over 4s are easy, right? That's a root 2 over 2 there. That's a root 2 over 2 there. 5 pi over 6, pi over 6 in the reference angle, still in quadrant 2. But now I'm looking at this angle here, right? There's my pi over 6 reference angle. Cosine of pi over 6 is negative root 3 over 2 because we're in quadrant 2. Sine of 5 pi over 6 is positive 1/2. This is going to equal negative root 6 over 4 plus root 2 over 4. I would not write it as negative root 6 plus root 2 all over 4. I would write it as root 2 minus root 6 all over 4. If one of them happens to be positive, I would write that one first. Let's see, I haven't done on time here. Okay. Yeah, if we, no, we don't have time. We'll do more examples in class. So the other thing I want to talk about is there is something called the double angle identities. So, and they're really easy to get to if you look at the angle sum identities. So I'm going to go back for just a second. So if we look at this angle sum identities, I'm going to derive the double angle identities very easily. So the double angle identities look like this. So if I want to find, say, sine of 2 theta, I'm going to think of it as sine of theta plus theta. And then I'm just thinking of this angle is theta and this angle is theta. So it's going to equal sine of theta times cosine of theta plus cosine of theta times sine of theta. But these are really the same, right? This is sine times cosine. This is sine times cosine. So I really have something added to itself. And just like when you add 5 plus 5 and you get 2 times 5, or x plus x and you get 2 times x, when you add something plus something, you get 2 of that something. So you get 2 times sine of theta times cosine of theta. And that is the double angle identity for sine. We have sine of 2 theta equals 2 sine theta cosine theta. And I want to make it super clear. We're going to see an example of this in just a second, but I want to make it really, really obvious. Sine of 2 theta does not generally equal 2 sine of theta. There's probably an angle you can actually find it to make it work for, but it doesn't work for every angle, right? To be an identity means it has to be true for every possible angle. Okay, let's look at the same thing for cosine. So for cosine of 2 theta, which we're going to write as cosine of theta plus theta, that's going to be, well, let's see, cosine of theta times cosine of theta minus sine of theta times sine of theta. Or cosine times cosine is cosine squared. Sine times sine is sine squared. So we end up getting cosine of 2 theta equals cosine squared theta minus sine squared theta. Be careful. It's easy to confuse this one with the Pythagorean identity, cosine squared theta plus sine squared theta is equal to 1. But this is cosine squared theta minus sine squared theta. It is not equal to 1 in general. If you pick the angle for 0 degrees or 90 degrees, then it would work. But generally, it does not work to be equal to 1. Okay. So those are your double angle identities. Let's go ahead and verify for a couple things. And also, well, actually, let's show this first. So let's say, for example, I want to show that sine of 2 times theta does not equal 2 times sine of theta. We have to be careful here because for some angles, you could totally make this work. For example, if you happen to pick, what was I going to pick here? Yeah, if you happen to pick, say, theta equal to 60 degrees, I think it actually does work. Yeah, let's find out. So let's see. So sine of 2 times 60 is equal to sine of 120 degrees. Oh, no, it's not going to work. That's good. Good that it doesn't work. It shouldn't work. And sine of 120 degrees is root 3 over 2. And it is positive root 3 over 2 because we're in quadrant 2. Right, reference angle is 60. Opposite root 3. Hypotenuse is 2. Distance 1. On the other hand, 2 times sine of 60 degrees is equal to 2 times, well, sine of 60 is also root 3 over 2. The 2 times root 3 over 2 is just root 3. These are not the same. And they shouldn't be the same. On the other hand, it would be true for the same angle that sine of 2 theta is equal to 2 sine theta times cosine theta. So once again, sine of 2 times 60 degrees is, of course, sine of 120 degrees, which is equal to root 3 over 2. And 2 times sine of 60 degrees times cosine of 60 degrees is equal to 2 times, well, sine of 60 is root 3 over 2, as we just saw. And cosine of 60, well, sine of 60 is root 3 over 2. Cosine of 60, it better be 1/2. And then you get 2 times root 3 over 4, which is just root 3 over 2. And those are the same as they should be. And it works. It works for any angle, right? It's always going to be the case that sine of 2 times your angle is equal to 2 times sine of your angle times cosine of your angle. In a similar way, we could verify that cosine of 2 theta equals cosine squared theta minus sine squared theta for an angle like, I don't know, theta equal to, what are we going to pick? Let's pick something like, sure, let's pick 135 degrees. Seems, sure. 135 degrees. That'll be interesting. So on the left-hand side, we have cosine of 2 times 135 degrees, which is cosine of 270 degrees. And if we use the 4 corners of our unit circle, 270 degrees is down here. The point is 0, -1. So cosine of 270 is 0. Okay. then let's make sure that it works out. So then cosine squared of 135 degrees minus sine squared of 135 degrees. Well, my reference angle is 45 degrees. And I know that cosine of 45 is root 2 over 2, and sine of 45 is root 2 over 2. Cosine of 135, again, we're in quadrant 2. It's kind of hard to avoid here. So cosine of 135 is going to be negative root 2 over 2. But it's going to be negative root 2 over 2 squared. And minus, sorry, sine of 135 is going to be positive root 2 over 2. So sine squared is positive root 2 over 2 squared. A negative number squared does become positive. Negative root 2 over 2 times negative root 2 over 2 is going to end up being positive. Root 2 times root 2 is 2. 2 times 2 is 4. Minus root 2 over 2 squared is again 2 over 4. And 2 over 4 minus 2 over 4 is indeed 0. So this checks out. Cosine squared, sorry, cosine of 2 theta minus cosine, wow, words. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta for any angles you might want to pick. What else do I want to say here? Sure, a couple more things. There is an angle sum identity for tangent, and there's also a double angle identity for tangent. I don't particularly think we need to know it. I'm not going to ask you about it. I will certainly tell it to you if you want to hear it, but I don't think we need to trouble ourselves with that. But let's look at a couple more things. Let's look at some trig identities, because there are some interesting ones involving the angle sum, angle difference formulas. So here's a couple trig identities. So again, we're going to simplify down to one term. Let's start with the following. Yeah, I've got cosine of theta plus sine of theta squared minus 1. Okay, that looks bonkers. Let's multiply this out. So that's going to be, see, cosine plus sine squared is going to be FOILed out. So I get cosine squared theta. I get 2 times cosine times sine, right? I'd probably write this 2 times sine times cosine theta, and then plus sine squared theta. Right, you're getting cosine times cosine, and then cosine times sine, and then cosine, and then sine times cosine, and then sine times sine. So there's your sine times cosine and your cosine times sine. Minus 1. Okay. But cosine squared plus sine squared is equal to 1. So if I add these together, that's going to give me a 1. So what I really got now is 2 sine theta times cosine theta plus 1 minus 1. But the ones cancel, and we're left with just 2 sine theta cosine theta. But I still haven't really met the requirement of simplifying this down to one term. But then I can remember, oh, 2 sine theta cosine theta is equal to sine of 2 theta. So that would be the answer I would be looking for here. Let's do a couple more examples, and there's a couple more interesting things I want to show you. And yeah, I'm not too bad yet. All right, let's do 2 more of these. Let's say we want to simplify down tangent of x. Yeah, I'm going to use x instead of theta times, what have I got here? Cosine squared x. Yeah, that's kind of weird. So when I don't know what to do, I fall back on writing things in terms of sines and cosines. So I'm going to write this as sine x over cosine x times cosine squared x. I can cancel a cosine, or I can write this really as sine of x times cosine squared x all over cosine x. Cancel a cosine here and a cosine here, and I'm left with sine x times cosine x, which almost looks like 2 sine x times cosine x. And here's what you can do. You can multiply and divide by 2. So this is equal to 2 sine of x times cosine of x divided by 2. But then 2 sine of x times cosine of x is equal to sine of 2x divided by 2. Or as I would probably write this, 1/2 times sine of 2x. One more of these, and then we will do something slightly different. Let's look at this last example I've got here. I should point out there's not a lot to do with the double angle formulas, like with actual values. Like we don't use them to find sine or cosine of anything kind of new, really. But they do come up a lot when you're doing integration with some trig identities. And they're also just kind of good to know because sometimes it's worth simplifying something using a double angle or an angle sum or difference identity. Let's look at one more of these identities here. Let's simplify cosine of 2x plus sine squared of x, all divided by cosine cubed of x. It's kind of bonkers. I like the word bonkers, what can I say? So I'm seeing a cosine of 2x. Be careful. If people don't write the parentheses, it can be really, you have to be super careful to, like, if I wrote on the side here, cosine of 2x versus cosine squared of x, you have to kind of really pay attention to the placement of that 2, right? If it's written in the superscript here, we mean squared. If it's written in front of the x in the same line, it doesn't mean that. I would definitely recommend using parentheses in these to really make sure it's clear where that 2 is living. Okay, so cosine of 2x is equal to cosine squared of x minus sine squared of x. Oh, don't forget the other plus sine squared of x here. All divided by cosine cubed. The sine squareds cancel. Minus sine squared plus sine squared is 0. So I'm left with cosine squared of x over cosine cubed of x. I can cancel out or divide a cosine squared and a cosine squared on top and bottom. I'm left with 1 over cosine of x. And then finally, I should write 1 over cosine as secant of x. Okay, couple more interesting identities. Yeah, let's do that one first. So there's an identity for cosine of negative x, which you might think that doesn't seem like you can do anything with it, but we can rewrite this as cosine of 0 degrees minus x. And then I can use my angle difference identity. Cosine of alpha minus beta is cosine alpha times cosine beta plus sine alpha times sine beta, and write this as cosine of 0 degrees times cosine of x plus sine of 0 degrees times sine of x. You see my unit circle here. There's 0 degrees. The point is 1 comma 0. So cosine of 0 degrees is 1. Sine of 0 degrees is 0. 1 times cosine is just cosine. 0 times sine is just 0. So what we end up getting here is that cosine of negative x is actually equal to cosine of x. So for example, if you ever had to like find, say, I don't know, cosine of negative 120 degrees, you can just be like, okay, James, instead, I want to find cosine of positive 120 degrees. And that is a valid move you can make. It's always true that cosine of a negative angle is equal to cosine of the corresponding positive angle. In a similar way, you should take the time to show that sine of negative x, which is equal to sine of 0 minus x, you can show with some work, and you should do the work, this is equal to negative sine of x. It's kind of cool. Let me give you one more. I have to remember what, let's see, let me just, I have to remember what it ended up being. Sure, yeah. I think I want it to be, let's see, I'm trying to think about sine. I want to shift it to the right. No. Yeah. I want sine of x plus pi over 2, or 90 degrees. So I'm going to show you what this is equal to. So this is going to be sine of x times cosine of pi over 2 plus cosine of x times sine of pi over 2. In the same sort of way, well, cosine up here at pi over 2 at the point 0, 1, cosine of pi over 2 is 0. And sine of pi over 2 is 1. So I end up getting just cosine of x. So sine of x plus pi over 2 is equal to cosine of x. It's kind of neat. It just really shows that sine and cosine are transformations of each other. Sine is just, or cosine is just sine shifted pi over 2 to the left. In a similar way, and again, I would encourage you to do this on your own, you can show that cosine of theta minus pi over 2 is equal to sine of theta. I think it's worth doing. I'll probably ask you to do it on the homework assignment anyway. And let me just double check. That's cosine theta, cosine pi over 2. Yep. Plus, yeah, that works out. So there are some identities for you. It's good to practice these. It's good to kind of know how to work with the angle sum, angle difference formulas to make things look like other things. All right, that is enough for class O.